new language that I've been working with. It's a kind of a companion language for Lua. I will explain that all along the talk. So one of the main ideas of Lua is to be this idea of scripting. This really not scripting just like any dynamic language, but scripting in that sense of the scripting architecture. You have a scripting language and a system language, and then you can write things in scripting, the things that need to be more flexible and more related to end users, and usually you write the hard parts of the application in the system language, and they communicate. And so there is a very common motto in scripting that if it's slow, rewrite it in C. So the main idea is that C is much faster than Lua, and you have both languages, so the critical parts of the performance critical parts of your application, you should read that in C, and the rest of the application you can read in the scripting language, Lua in our case. But that idea of rewrite it in C, it's much easier said than done, because we have several problems. In particular, we have a big problem of data mismatch and a problem of language mismatch. Data mismatch is that Lua has its own data structures, and they are abstracted away. You don't have direct access to them. You should not have direct access to them because you could break them, you could break the invariants, etc. And so we need to transfer data. Anything we want to manipulate in C, we want to transfer to C, or we can keep that data and C, and then when we want to manipulate that in Lua, we have to transfer the data to Lua, but all the time you are transferring data between the two languages. And then, of course, you have to convert doubles you don't have to convert, but you have a list or even a string. Sometimes you have to change the memory allocation of how the string is allocated in Lua, how it's going to be allocated in C, etc. And this process can kill any gain in performance that you could gain by changing something to C. You implement that in C. If the C is doing something very small, and there is a lot of data transfer between C and Lua, then sometimes the reimplementation in C can be even slower than the original in Lua. And of course, there is a big difference in language between Lua and C. And it can be very expensive. I mean, if you have just a short function, it's easy to rewrite in C, but you have to rewrite larger parts of your application. It can be very expensive to change that from Lua to C. And maybe what is the worst part of all that is that it's very difficult to predict. As I said in the other slide, it's hard to predict whether it's worth re-implementing something in C. So sometimes you can spend a lot of time converting everything to C, etc., doing a lot of work, and then at the end you realize, oh, I'm not gaining anything, or I'm gaining very little from all that effort. So as I said, that's not very easy to just say, oh, it's so slow, just change to C and everything, it solves all your problems. And so one solution people have been using for a long time, of course, is JITs, just-in-time compilers. It has some very good things. In particular, apparently you don't change the language, and you can achieve really good performance. Lua JIT is a very nice example that for some programs you can achieve excellent performance. But on the other hand, JITs are much harder to implement, to port, and to maintain. Again, Lua JIT is a good example. And so we would prefer something simpler, in particular more portable, more in line with other Lua goals. And also JITs has these famous optimization killers. All kinds of JITs had these problems that I mentioned in the other talk about performance, that some things can be very fast and sometimes you just change something little and then you break some kind of optimization that you didn't know about, and then suddenly, because of one or an extra semicolon, I mean, exaggerating, but some very small change in your program, it's running 3 times slower than it was. I mean, it's not 5%, but sometimes really 3 times, 4 times slow because it's not optimizing that part or it's not even compiling that part. So it's very hard to predict the performance. And what happens is that, and that happens not only with Lua JIT, it happens with JavaScript, with V8, and any kind of those JIT compilers. Programmers go to great lengths to appease a JIT. As I said, you start to develop dialects, you know that thing is how you must write that thing. You cannot use exception handling, or you cannot use that or that. You must write your program in that particular way. If the function has 4 parameters, it's great. If it has 5 parameters, then it breaks something else, and etc. And so you start almost to create a dialect of the real language to program to have good performance in a JIT. And so it brings the question as if you're already creating a kind of a different language, you are available to use to learn a different language. So at what point it would be a good idea to switch to a type of language? I mean, to really create a different language instead of just using the language in very particular ways. So what is Pallene? Pallene is as I said, is a programming language, and it's strongly based in the idea of scripting. So it's been designed to act as the system counterpart of Lua in that scripting architecture I talked about. So the idea that instead of writing your programs with part in Lua and part in C, you'd have it parts in Lua, parts in Pallene, and maybe some parts in C. We'll see later. Pallene should be very easy to communicate with C. And but the idea is that that language, it should help bring the gap between Lua and the system language. So to reduce the language mismatch, I mean the effort you need to change your program from Lua to the system language, to Pallene in that case, Pallene should be a subset of Lua as a language. I mean the constructions of Pallene should be like Lua, except that with types. And that may be the main idea, is to reduce data mismatch. Pallene operates directly on Lua data. Pallene doesn't have its own data structures, is a language that is implemented on top of the Lua runtime. So the idea is that but at the other hand, it works exactly as a scripting like C. So you compile a Pallene module, you generate an object that you link with a Lua standard Lua interpreter, like you could link any other C module. I mean, so it interoperates with Lua in the very natural way as we are doing, but you program it in a very different way than you program C extensions. So Pallene, this idea of gradual typing, as I said, Pallene this is a Pallene code. As I said, the idea is to be a subset of Lua. If you remove the red parts, that the type information, then you have just a Lua program. And so what the idea of types, this is maybe a very big point of Pallene, that types in Pallene are for performance. So we do not have this, for instance, when you see this idea of gradual typing, of adding, that's a big problem of adding types to dynamic languages, is that you want the type system to be able to express everything that you want to write in the scripting language. And so the type systems for those languages usually are very complicated, they're very hard, they have all kinds of polymorphisms, all kinds of exceptions, sometimes they are not safe. There is a whole bag of complications on adding types to dynamic languages. And in the case of Pallene, everything is much simpler because we only want to add types for performance. If types cannot bring you performance, you don't need to add types. We don't have the types to add. I mean, you just have basic types that express what we know can easily be done efficiently, like arrays, records, and things like that. And in particular, the type system itself, a big part of the subset that Pallene is a subset of Lua, a big part of this reduction of things that you cannot express in Pallene is due to its limited type system. So for instance, of course, all that can change in the future, but for now, for instance, we don't have meta methods. So we use tables in tamed ways. So for instance, that table is going to represent a regular array of floats. And that's it. We assume that table is an array of floats. It has no meta method. If there is anything different from a float inside the array, it's an error. So we can generate, as I said, we can generate efficient code easily. We don't have variadic functions. We don't have coroutines for now. And that's what I said, that with the tables, we only have tamed forms of tables. We don't have generic tables like in Lua, but we notice that Pallene accesses the real table in Lua, but it assumes, I mean, it do all the checking, is a safe language, but it assumes if the table is not as it should be, it is an error, and that's it. It doesn't try to recover, to go to an interpreter to do dynamic stuff, etc. If it doesn't satisfy the written types, it's an error, and that's it. And of course, even for this simple typing system, you have there's a lot of subtleties because of this idea of exactly that it operates on Lua data. So the data itself, mostly data structures, are never really typed. The type, as I said, is what Pallene expects to find there. So this is a very nice example. You have an identity function for arrays of floats. So this is it should be a Pallene program.
Is there something missing, or is it intentionally?
I think it's correct. Local function ID, this is the name of the function. There is a parameter A, which is of type is an array of floats, and it returns an array of floats. Yeah, the semicolon after is the return type of the function, and then just returns its only argument. So this, as I said, it's an identity function for array of floats. And this is a nice example of things that types can worsen your performance. Because without types, you just return what you get, and that's it. You don't have to do anything. And with types, it brings the question, should we check the types? So what's the correct semantics of that function? Should it really demand that it receives? So here are some examples. From Lua, I call this function. So I call with an empty table. That's an empty array. It should be correct. I call it an array of the second example. I call it an array of floats, of course, if correct. But then, for instance, if I call it an array which has a hole, then nil is not a float. So should the function bring an error, throws an error, or just ignore that, returns ignore the type, or the second line from the bottom, I forgot the English word for that. If you pass a number, should it waste time checking that it got a table, or just return the number? So as I said, that there is this, currently we use something that it's called transient types. I don't know why it's called that. And then it should give an error in this second to last example, but it would not give an error in all other cases. So it mainly checks that I got a table. It's a table, it's good enough for now. So, but anyway, it has to do a check. It's a very fast operation, but it's slower than not doing the check. So the type in this case, it's a, but so the point here is that even for a very simple type system, this idea of of integrating a dynamic language with a typing language, it brings all that kinds of subtle questions of what happens in the borders, etc. So just to emphasize again, a big point of Pallene is that it uses Lua data structures, just as I said, in tamed forms. That means, for instance, if you say that is an array of floats, it expects that to be an array. It can even call internal functions from Lua to force the array to be in the array part of the internal representation of tables. So the code that Pallene generates can operate directly on the array internal representation of the table. So it has complete access to everything internal to Lua, but it uses only the Lua regular data structure. So of course it reuses Lua garbage collector. Pallene knows about the garbage collector. It knows where it has to keep barriers, or where it has to insert calls to the garbage collector, etc. So it ensures that the code is consistent with the garbage collector. And that's a big point, because of course you cannot give that kind of direct access to programmers in C, because it's almost impossible to document that, and then there will be a whole lot of bugs because people are not using the things properly. But here the compiler creates the code, so the compiler is responsible to ensure that the code it creates respects everything Lua data structures expect to how to keep the data structure consistent all the time. And so, of course, how types help, that's maybe the main difference. I mean, the JIT serves as an inspiration for us. We wanted to have something like JIT, but exactly adding types makes, of course, we gain performance, but the main point maybe is that we gain simplicity. When you compare Pallene with JIT, we see that types make things much, much simpler. So some things to consider for performance is that one thing is that there is this general idea sometimes that tag checking is expensive. It's very common that you say, oh, scripting language, all values have tags, you have to check the tags every time you access. Checking tags is not expensive. That can be 3% of 5% is a huge cost for tag checking, and you can pay 5%. I mean, the problem of scripting versus non-scripted language is not 5%. It's 3 times faster, 10 times faster. So you can do, so it's 10 times faster minus 5%. That's very, very, very good. So tag checking is not the problem. For instance, JIT, most JITs do tag checking all the time. They have to check the data they are reading, have the expected type, and so they do not eliminate tag checking. What is expensive is boxing, unboxing. What is expensive in interpreted languages, you don't know what the type is, so you don't know whether you can keep that in a register, you don't know whether it's 64 bits, 32 bits, or is something larger, etc. And so everything you have to represent with indirections, and it's really where you can have huge gains if you can keep things unboxed inside registers, inside regular variables in C, etc. And so the main idea of types is to guide this boxing, unboxing. As I said, when you access the array, you don't know what we are going to find there, but you know that you want to find a float, and once you check that the tag is a float, you store that in a float variable in your target language, and that's it. If it's not a float that is there, it's an error, and you are finished. And after that, you can manipulate that float value, unboxed all the time as a native float, a native double in the rest of the code. And so what brings simply, if you compare that with JITs, there are two main goals. One, of course, you don't need to deduce types, you don't need that either a simpler compiler to first compile the language with generic types and then you recompile that with more specific types, or you first interpret the code, then you gather types and then you deduce, oh, that function is only being called with integers, so you create code for integers. That's a big source of complexity in JIT compilers. And if you just up front you say this is going to be an integer, it's a little more work for the programmer, and it's a huge part of the compiler that you can eliminate. And second, that I think it's really the worst part of a JIT compiler is that you don't have to recover from errors. A JIT compiler, it assumes, oh, this is going to be a double, and then it creates very efficient code for double. As I said, it doesn't eliminate type checks, the tag checks, it has to do the tag check. But if the tag is wrong, then it must unroll all optimizations, transfer all state back to the interpreter to continue executing the code correctly for an unexpected type. People don't show that in benchmarks. Benchmarks are very predictable, things are very, but in real code, or even if you never use that code, it must be there, it must be correct, and this is a very huge source of complexity in JIT compilers, how you transfer the whole optimized state in any point of your program. Anything that goes wrong, you have to recover everything back to either to the unoptimized compiled code or to the interpreter and continue executing as if nothing happened. And when you put types, as I say, that should be an integer. It's not an integer, error, dot, finish, nothing else in your code to worry about. So as I say, it's a little effort for the programmer, but the implementation is much simpler. So the design principles that we are following in Pallene, as I said, I think the main point is that it has the same selling points as Lua. So it wants to follow the same ideas that the direct Lua. I'm going to talk a little about that. And it has a very simple ahead-of-time compiler. I'll talk about all this. A very simple type system that I talked a little already. It's good on the borders, the borders between Lua and Pallene. It should be very efficient. You shouldn't have to worry, oh, should I put that function in Pallene bill? I have to pay some price. There is no price at the border. And we want to keep what is called the gradual guarantee that I explained that. So selling points, as I said, it's portable, small size, simple, and emphasis on scripting. So the idea of Pallene is that it should generate C code following the same standards, the C code from Lua. So once you compile that to C code, should be compilable in a C compiler. In any platform that supports Lua, you should be able to use Pallene. Even if you have to compile Pallene itself in a different machine, you can get the C code it generates, put in any target machine, and should be as portable as Lua itself. And so, as I said, a very simple ahead-of-time compiler. It generates C code. It simplifies the implementation. A lot of the optimizations we don't need to worry about because the C compiler will do many optimizations. Of course, there are several optimizations that Pallene should do because the C compiler cannot know enough about for instance, when you call the garbage collector, is a very nice example. For C, that means we can change everything in the world. That means external call. And for C, that means I don't know whether pointers are still pointing to where they were, etc. So a C compiler lose all information it has about the code when you call a foreign function that it knows nothing about. While the Pallene compiler knows, I'm calling the garbage collector, it can do a lot of things, but I'm sure it's not going to change anything that I'm touching now, so I can be sure I can keep things if things are anchored somewhere else, I can keep things in registers, I do not need to split the registers, etc. So Pallene can do a lot of the optimizations, but there is a lot of optimizations that it doesn't have to do. As I said, it's a very simple type system. It's not the goal of the type system to be able to express all marvelous things you can do with polymorphisms in Lua. So we just want to express what can be efficient. What cannot be efficient, there is an any type in Pallene, so you can convert any to anything else or anything else to any. So any kind of polymorphisms that you want to represent in Pallene, you just put any and that's it. Or better yet, you just keep the code in Lua because you are not going to gain any. Probably you would not gain performance in a JIT compiler either if you put that specific, that a lot of closures and a lot of higher order functions, etc. You probably wouldn't gain much performance or even any performance in the JIT compiler anyway. And here it's very clear that I can assure you that I'm going to generate, if you can write that in Pallene, as I say, there are very simple data structures, you are sure it's going to generate good code. And as I said, a very important point of Pallene is to be good on the borders. That I have a strong idea in gradual typing of those languages that have optional types. Usually they have this idea that you add types and after a long type your whole program will be typed, and then you get the holy grail that you have a complete typed program, and then maybe it becomes efficient. But most programs don't do, they are not static, they are sitting waiting to be typed. Programs are changing all the time, and types exactly are hard to change. The main idea of dynamic language is not having type is easy to change. So the idea is that you really want to add types only to make static, really static, only the parts of the program that are more performance sensitive. Usually these are the parts that change less in the program exactly because you you spend a lot of effort optimizing that, etc. So you don't want to change that naturally. And so most programs have some parts that naturally would have some parts typed and some parts untyped. And as I said, if you not get good performance switching between the typed part and the untyped part, then maybe you don't gain much at all. And this is something that we try to get. There is a lot of subtleties here that is called the gradual guarantee, that the Pallene function should have the same semantics as the translation to Lua except for type error. So you have a Pallene function and it works without raising a type error. If you remove the type annotations, then it should work the same way in Lua. And that, again, is a whole can of worms. There is all kinds of subtleties. For instance, a big discussion in Pallene is whether you should do coercion from integers to floats, because if it does that, then you lose the gradual guarantee, because if you have something that is coming as an integer and it's because you said the variable is float, then it's converted to float and everything else is working on a float. If you remove the type information, then in Lua that continues to be an integer, and so you can have different results. So there is this is something that we are still discussing, how much of the really want of the gradual guarantee we want to enforce, because sometimes it can be not practical to be so strict about the gradual guarantee. And so here I have some performance, just a few benchmarks. So this is comparing standard Lua that is normalized to 1 unit of time. And then you have Lua using the C API. Lua using the C API means we re-implemented these are very small benchmarks, so we implemented the benchmark in C, but using the data structures in Lua through the official Lua API. This is the dark blue. Then you have LuaJIT in yellow. Then we have Pallene in green, and C, this is just we write everything in C using C data structures, etc., just as a kind of, that's more or less as fast as we can. And so, as I said, I think a big insight from this is the dark blue. As I said, that just changing to C, sometimes you can get, for instance, in the, what's that name? In the Queen example, you can get a huge performance gain. In binary search, you have a big performance gain. But in some other examples, you don't gain anything, or you even lose performance when you just translate the code to C using the C APIs, mainly if you translate just small functions, etc. And then you had the other important thing here is the comparison of yellow and green, that's LuaJIT versus Pallene. So we see that they're more or less on par. In the Conway, the LuaJIT is much worse, but it's just because of the garbage collector, because the Lua 5.4 has a better garbage collector, so everything that is better in the Conway, everything is better than LuaJIT, but it's only because of the garbage collector. It has nothing to do with the real code there. On the other hand, on matrix multiplication, there is the example that JIT is faster than Pallene by a larger fraction than the other examples. That's because of the non-trick in Lua JIT. Here then the problem with Pallene is the memory, mishits in the cache. So Pallene lose more time reading from memory than Lua JIT, because Lua JIT use half the memory, and so it has to read half the memory to run everything. This is something that I'm working really hard in Lua, and Pallene would benefit from that to use reduced memory for arrays. But we're still not there, because this non-trick that we cannot use in Lua anymore really reduce memory, and reducing memory you reduce time, because you don't have to read that many stuff. Again, that's funny, as I said, in all these examples I didn't show here, but if you, as I said about the tag check, if you remove tag checks, we assume, I know types are going to be correct in these examples, so you can create Pallene code without checking the tags of anything, just read, and I'm sure that's going to have an integer there, etc. And the gains are, sometimes the gains are 0, because exactly that's CPU time, and the CPU is don't matter the word, but okay, the CPU is waiting for memory, so it has extra time to waste. So check the tag without, and the tag is just near that, so it doesn't waste time reading the tag, also because it's there in the cache anyway. So in some examples here, you remove tag checks and you gain nothing, literally not a single CPU cycle more efficient if you remove type checks. But if you remove memory, then you have some gains. But you see that the main point is that you have something that is on par with JIT. I mean, our point is not to be better than JIT, but to be comparable with JIT, with a much simpler effort. It's much simpler code, much more portable code than JITs. And this is a very nice example. That's about the borders that we got those 4 benchmarks and broke them in small, but mostly they are the main functions of the benchmark. So it's not a circle, each oval, each egg there is one represents a function, and when the egg is white, it represents the functions written in Lua, and the black represents the functions written in Pallene. So we have all kinds of combinations that we have. So for instance, here you have the whole program written in Lua. Here we have two functions still in Lua, one translated to Pallene. Here we translated another one to Pallene, etc., etc. And at the top we have the whole program in Pallene. And this is time. All times are one is the unit for. So you see that anything in any benchmark that you change to Pallene, you gain something. It can be very small fraction, but you never lose performance when you change even a very single function inside your program to Pallene. So you can change gradually your program without that, oh, that change was not good because that, etc., etc. So you have this confidence that whatever is going to type, just type that and you gain a little performance, then you can type something else and you move, as I said, the critical parts of your application to Pallene. So the conclusions is performance is always present concern, and as I said, this is for now Pallene is more in a stage of a proof of concept. It's not near to be ready for use, for real uses. but we want to explore this idea of having good performance without the huge complexities involved in JIT compilation that we really think it's really hard and shouldn't be that hard to get some good performance gains. So that's it. Questions?
How usable is Pallene right now? Like, is it close to a stable release or?
Pardon me?
How usable? How close to a stable release is it? The Pallene compiler.
How close to?
To a stable release.
Oh, to a stable release. Sorry, I understood table. Stable release. Not close. Yes. There was this problem. There was this little pandemic in the last 2 years. So now we are really trying to even the team got dispersed. The people traveled, returned to their hometowns or went to other places. So now we are trying to more or less restart working more or less consistently on the project.
So if you have a question, you get a microphone.
Oh.
Yeah. Thank you. Regarding the type attribute, so is it optional? So for example, if you have a type that cannot be optimized like a table, nested table, so is it optional to specify it in the parameter list of a function? So
that's the idea of being a different language.
Okay.
If you're writing Pallene, then you must put the types, all the types in parameters, the result type, everything must be typed. Even if you may type with any, but you have to write the type any, that means anything. And to use a value of type any, you must explicitly cast that to the type. You cannot get a thing that it's any and add that to another value. You have to explicitly cast that to an integer or a float and then add, etc.
So, for example, if you have a specific example, if you have a table, like a nested table, then in this case you would write any. Or would you specify the table itself, including the nested tables in the type? No.
Yeah, you have a table, so you have an array of arrays of, you have.
So can you, how is this type written then? I mean, if you have, for example, a table with several nested tables and all of them have some members, how is the type written syntactically then? Like the Lua structure? Okay.
This, for instance, is an array of records with fields X, which is a float, and Y, which is a float.
So I assume the optimizations really happen in this case.
Yes.
Yeah. Okay.
Exactly.
Thank you.
And as I said, that's the kind of types that you can write. You cannot write other types because you cannot, for instance, heterogeneous arrays that can have different kinds of stuff. You cannot optimize that. You cannot write that type. Just don't use Pallene or say you can write that, for instance, an array of any. But then, as I say, every time you access an element, to use that element, you must explicitly cast that to some other type.
So I was wondering, so for now, I think to use Pallene, you need to use a special fork of Lua, which exposes the internals. Do you intend to add this to standard Lua so you can use Pallene modules with standard Lua?
We intend to, now there is this problem that we intend to get rid of that and be able to use Pallene with regular Lua, without changing Lua. I mean, it should be possible to use Pallene, as I said, just creating the same way we use regular C modules. It should, so there is some problems that, or maybe we will have to change something in Lua, but I still expect that we shouldn't need to change anything in Lua. You just could use standard Lua. One thing that's very important that I forgot to mention, but that's more or less obvious, that the compiler, it's very sensitive to Lua versions because it manipulates everything inside Lua. So if you change a single field in an internal structure of Lua, you have to use a different, the Pallene compiler for that specific version of Lua.
But do I understand this correctly? Well, I must say I'm not interested in JIT. At beginning I was. So when I looked at Lua, I thought, oh, in worst case we can look JIT, but then I recognized that Lua is so fast that it doesn't make sense for us to use JIT. But if you use JIT, you are still fully flexible with the code. So you can say your end user, just give me an ASCII file and my software will do it. But if you use Pallene for some, then Pallene has to be sort of precompiled. So you lose flexibility. So the end user cannot use Pallene. It's somehow for the core developers.
That's true, but there is some points here. One is that one, as I mentioned, that it's very difficult for end users to get good performance from JITs. Because as I said, you have to be more or less careful when you write JIT. So JIT, it gives you flexibility and it gives you performance, but not at the same time. Usually you have to you have to be, as I said, for instance, if you start using a lot of data creation, for instance, then you have problems with garbage collection. Garbage collection eats everything, and so it doesn't matter whether it's JIT or not JIT, and everything is, it goes down to the collector. And if you use a lot of closures and higher order functions, JITs also don't be good. And so I think that the main point here, you have to be careful, is that with Pallene it's easy to increase your library, that what you can provide for users. And so users can have more primitives, etc.
So if you have a sort of ingenious user who made a very nice library, you can put it into the core then.
Yes.
Yeah, that's a good decision then. Yeah. Okay.
Yes.
Okay,
but this is a nice point, yes, for that kind of things that you want to expose the users, and you expect the users to know how. Some places need that. That's true. That the users, you can expect users to be knowledgeable enough to get the benefits from a JIT.
Some time ago there was or still is a Terra language which seems to aim to the same goals of there being a companion or typed companion to Lua. So how Pallene does compare to it?
I think Terra is, it's quite different because Terra is not intended to be used that way, literally. Terra is more like you use Lua to generate Terra code, and then you run Terra more or less independently from Lua. I think that the goals are very different. Terra is very driven towards high performance. And so you want to write an application, then the main idea is that a lot of things depends on the architecture, etc. And so you can use Lua to configure the code that you are creating. and then you create that code. It has some limited capacity of communication, but it's not the emphasis of Terra. It's not for the final program that you create to really be run together with Lua as like Lua modules, or of this idea that you really have a Lua application with some parts of many parts written in another language. This idea of scripting architecture.
There is also another language, MoonScript. Can you explain the difference?
I know the name, I read, but I never read deeply enough to discuss anything about that.
No, MoonScript is not really related to this. MoonScript is like a CoffeeScript for JavaScript. So it's like a different syntax to generate Lua. It compiles to Lua. So it's not really this kind of thing. The language that maybe you're thinking of is Titan, which is like a kind of predecessor to Pallene. Like it was a different. I think it was almost the same language at some point. There was a language called Titan.
Titan.
Oh, Titan,
Yeah.
yes, Titan. Yeah, Titan was Pallene is a kind of a fork of Titan because we wanted to keep it more academic, because Titan had this idea of going to market fast, and we had this idea of studying and seeing what we can. So Pallene is a kind of academic fork of.
I had a question. Would a program that does a lot of C function calls benefit for Pallene, or is it mostly for Lua computation inside Lua?
Pardon? What's?
Sorry?
I didn't understand the
sorry,
question.
sorry if I...
No, I understand. You said the Lua calls C functions,
Yeah.
but what's the question?
Like, would Pallene benefit that type of programs, or is it more for just computation inside Lua?
No, it should be. There is two uses there, because one is just to replace C for those kinds of stuff. You just can write those. For instance, you could write a lot of Lua libraries, the standard libraries that are written in C. They could be written in Pallene. But also, I forgot to mention that in the type. Because Pallene generates C, it's very easy to do a foreign function interface from Pallene to C. And so it should be much easier to call C, for instance, you have a C function, C library, and to build the interface between Lua and the C library with Pallene. Because you just write an intermediate function in Pallene. Pallene has direct access to all data in Lua, and then in Pallene, this foreign function interface does the stuff then it converts data to C, call the function, and back, etc. So Pallene also has this goal of being used as a kind of glue language between Lua and C, because it talks well both with Lua and with C on both sides.
All right, thank you.
Thank you again.